Welcome to one of the mini lectures for Module 9. In this mini lecture we're going to be looking at one-factor repeated measures ANOVA. In this module you should be able to understand the conceptual background for one-factor repeated measures ANOVA and for factorial design ANOVA. Note that for this module I will not ask you to calculate the sum of squares for these ANOVA designs or to conduct two-keys tests. This is because these are slightly more advanced topics in ANOVA, and I want to make sure that you have the conceptual basis, but you don't have to do all of the calculations. So you should be able to understand partitioning of variance, determining degrees of freedom, how to interpret the f-values, and the advantages and disadvantages for a one-factor repeated measures ANOVA. And then for a factorial ANOVA, be able to interpret graphical output, understand how interactions work, and the restrictions and limitations for the factorial ANOVA. When we do a one-factor repeated measures ANOVA, this combines elements of a paired design with an ANOVA analysis. So we looked before at doing a paired t-test when you had one subject and maybe you had before and after data. So it combines this idea of a paired design, but we might have multiple scores per subject or multiple measurements. So maybe instead of having just a before and after, we have a before measurement immediately after something and then at some point in the future. So keep that in mind. Conceptually, for repeated measures ANOVA, we have one factor with at least two levels. If we had only two levels, we would be doing a paired sample t-test. And these levels are not independent, meaning that they share variability in some way. So if we have repeated measures on a particular individual, for instance, over time. Okay, so the levels are not independent because we have measurements taken on the same individuals. For our statistical hypotheses, these are the same as a one-way ANOVA. So our null hypothesis is that the means are the same, and our alternative hypothesis is that at least two of the means differ. And we use a one-factor repeated measures ANOVA when the same subject is measured multiple times under different conditions. This is known as a longitudinal analysis, so following individuals over time. And this idea of having one factor means that we have one independent variable with multiple different levels. Okay, so this is also similar to a one-way ANOVA. So you might hear one-way ANOVA or a one-factor ANOVA. Just means that there's one independent variable that has multiple different levels. So this could mean that there's different drugs, for instance, administered to the same person. So there might be 4 different drugs that are tried at different times. We want to control for that variability just associated with the fact that we'll have multiple different people in our study and that they're not independent. So we'll work through an example with this one-factor repeated measures ANOVA. So there was a study done to determine if a new treatment for attention deficit disorder was effective, so ADHD. Step 1 is to construct our statistical hypothesis. So we have our mean pre-treatment value, then we have our post-treatment value, and then after a 6-month follow-up. And I'll talk a little bit more about this exact experimental design in a second when we get to the data collection part. And our alternative hypothesis is that at least 2 of these means are going to differ. So keep in mind that for the independent variable is treatment timing, and we have 3 different levels. We have before the treatment for ADHD was applied, right after the treatment was applied, and then 6 months later. And the dependent variable is what we're measuring, which is level of distraction. So we're going to have the same individuals that we're going to have pre-treatment measurements, post-treatment measurements, and a 6-month follow-up measurement on. So step 2 is that we establish our statistical decision rule, and we'll use an alpha of 0.05. And step 3 is to calculate our test statistics. So the first thing we have to do is collect data. We're going to have 4 children with ADHD, and we're going to measure their level of distraction. So higher values means that these individuals are more distracted. And then each student underwent behavioral therapy for 3 months. And then the level of distraction was assessed at the end of those 3 months, and then again after 6 months. That level of distraction was assessed once again. So in this case, we have data on the same child for each time period. So the initial, at the end of the treatment, and then 6 months later. So this is a longitudinal study. And because we're following the same individual over time, we don't have a number of different independent samples here. So we need to keep track of our individuals that we're following. And here's our sample data set. So we have pre-treatment, post-treatment, and a 6-month follow-up. Keep in mind that higher levels mean more distraction here. The bottom row is just the means for the different columns. And what you can see is that the highest level of distraction tends to be in the pre-treatment phase, and then the lowest is in the post-treatment. When we look at the different rows, we see that there's a lot of variability, and this variability is just related to the participant that we're looking at. Some of the causes for this variability could be that some individuals, so participant 1, has less severe ADHD. Maybe an individual had a good night's sleep before they went and took the test. Maybe the teacher taught to the test. There's all these different, all this variation that might influence participants. And we would expect that not all individuals are the same. So it's common sense to expect that we're going to see differences just due to the different participants. And that's not really informative to our question of whether or not this new methodology to treat ADHD is effective. So we have our data here. Again, you don't have to know how to calculate all the sum of squares and everything like that. But you do have to know how to partition the variance. So when we do a standard ANOVA, remember we have our sum of squares total, and some of this is due to the treatment effects, and some of this is due to just random sampling error. So when we do our repeated measures ANOVA, we have our sum of squares total. Some of that variation is just going to be due to subjects, right? We're going to expect that. But then the variation within subjects, when we're looking at the effects of the treatment over time, are going to be due to the treatment effect and then just due to error. So in repeated measures ANOVA, we have the variation due to the subjects, due to the treatment, and due to the error. There's 3 components. When we calculate the test statistic, we are going to look at an Anova table. So here we have the sources of variability in the left-hand column. So we have variability just due to the subjects or the participants, and the sum of squares value. Our degrees of freedom is how many individuals we had, how many individual subjects, which was 4 minus 1 is equal to 3. Then we have the treatment effect, our sum of squares associated with that. It's k minus 1. So we had 3 different treatments. So we had the initial pre-treatment, we have post-treatment, and a 6-month follow-up. So that's 3 minus 1 is equal to 2. And then we have the error. We have our error sum of squares, and our degrees of freedom for this is based on the degrees of freedom for the subjects times the degrees of freedom for the treatment. 3 times 2 is equal to 6. And then our total is at the bottom. And the end total is, when we look at the data table, there were 12 cells in that table, right? We have 4 individuals times 3 time periods. That's 12 minus 1 is equal to 11. The mean square is calculated similarly to what you've seen before. So it's a sum of squares divided by the degrees of freedom. We only calculate this for the treatment and the error. And then our F statistic is our treatment mean square divided by our error mean square. So our F statistic is 18.72. The subjects, again, we just want to keep track of them, but they do not actually factor into our F statistic that we have. And then finally, we want to compare the test statistic with the decision rule and draw a statistical conclusion about our null hypothesis. Our F statistic is 18.72, and the degrees of freedom that we use is 2 and 6. We use this to go to the F table and look up the values. You know how to do that from a previous module. These degrees of freedom are based on the treatment, that has degrees of freedom of 2, and the error, which has degrees of freedom of 6. Our F critical value from the table, based on 2 and 6 degrees of freedom, is 5.14. Our F statistic is 18.72, which is out in the rejection region. Therefore, we reject our null hypothesis and conclude that at least two means differ. From here, you could go on and do a Tukey test to figure out which of the means actually differ. Again, you will not be expected to do that for this module.